Right, so thanks for coming. So this week we have Magnus visiting us, and he'll talk about linear delta matrix and algorithms.
Thanks for inviting me. So I'll be talking about representations and algorithms on linear delta matrix. This is a joint work with Edward Iben and Tomohiro Koana. So it actually will be mostly representation. Okay, we'll get it. So to start somewhere at the beginning, so I'm not even going to give the axioms, just to kind of remind the, I don't know if there's anyone in this audience who doesn't already know what matrices are, but just to start somewhere. In a very non-precise sense, a matroid is a family of. Is the problem?
So the slide is not on the screen.
I mean, the picture is on the.
그건 문제는 아니에요. 채널 앞에 거죠?
그 프로그램 안에서
예, 프로그램 안에서는 맞는 거 같은데.
there's an issue with 이거 말고 카메라 문제요. 지금 화면 카메라가 아니면
슬라이드가 지금
그걸 디바이스 바꿔 한번 했다가 다시
이게 한 번씩 문제가 생기더라고요. 그건 나중에. 이게 잘 나오는데 이게 아니에요.
이게 그거 아니야? 비디오?
이게 참 아리까리한데 기억이.
아니 그거는 이게 슬라이드 아니 그거는 이게
Yeah, that's right.
아까 나왔다. 아까 잠깐
Are you running the YouTube?
I mean, this is.
Oh, that's there.
They are
그건
running.
Are you in charge of the chat? No.
I mean, I used to be
Yeah, I remember.
until
that.
nobody was chatting, so I stopped.
I think I did once.
Yeah,
I did,
I mean, back in the day,
Yeah.
yes,
Yeah.
but I mean, nobody's watching this live anymore anyway.
Really?
Yeah. think people
이게
still watch
지금
the
모니터잖아요,
videos.
그지?
Yeah, nobody watches.
모니터가
Yes,
아닌 거고.
yes, yes.
Except for all of
이거를
that's
I was watching live for a little bit.
이거 안 하고 갈라져야 되는데 연결 하나 안 돼. 이게 안 돼. You should chat. You should chat. 이게 여기
one message, so he feels
I
appreciated.
think
No, I
it's-
don't. It doesn't matter. I'm not looking at it.
Oh, I see.
the main shell one.
It's really not working.
이게 거기 임 꽂혀 있어요.
I was thinking
얘 그럼 어디 꽂혀? 얘가 인이잖아. 인이
Back in the day, it
컴퓨터.
was useful because people were chatting.
아 잠시만 얘가 아니라 얘가 꽂혀야 되는 거 아니에요?
다른 것도 같네. 다른 것도
I think
같네.
after 6 months,
이게 인으로 들어가야 돼.
네, 이게
이게
여기
모니터야. 거기
I-
그래야 들어가야 돼.
I-
그러네.
Let's get a link to ChatGPT or something.
맞네, 맞네.
Yeah, I asked.
Somebody remove the cable.
when you were watching this stuff. That's no 테스트를 안 해보고 시작했네. Problem solved.
Not quite.
Oh, I think he's fixing it. Yes, he's fixing it. Okay, should we continue?
Okay.
Yeah, okay.
All right, so yeah, so matroids can be defined, I don't know, half a dozen different ways. The two ways which are going to be tangentially relevant here are you can define them as a set family of independent sets, in which case one of the axioms is that every subset of an independent set is independent, or a family of bases, which is again a set family, and it has the property that all bases have the same cardinality. And yeah, famous example, graphic matroids are matroids over edge sets where the bases are edge sets of spanning forests. Co-graphic matroids have had at least one application for a kind of algorithmic application in FPT. The useful property is that independence of a, in that case, means that the edge set does not contain any cuts in the graph. And linear matroids being vector sets and so on. So for delta matroids, all I'm going to say about the axiomatization is that instead of talking about bases or independent sets, which have this kind of connotation that about the cardinality of behavior, you have some family of feasible sets with a useful exchange property, where independent set of matroids and bases of matroids are both special cases, and so are other cases. So this is something which generalizes matroids and covers a lot of additional ground. And as we said just before we started, in full generality, these are so general you can't really do much algorithmically with them. So I'm going to be talking entirely about linear delta matroids. And also I come from a background of parameterized complexity. The reason we're looking at this is kind of aiming towards consequences in parameterized complexity. So some sense kind of why do we want to use matroids in our algorithms? This is a biased perspective, but one reason is there are polynomial time algorithms which apply to all matroids or all linear matroids, and also some kind of min-max theorems which tell you the structure of what is possible and not possible. There's a greedy algorithm which always finds your max weight basis in a matroid, and there's intersection and parity. I'll get back to those. Within parameterized complexity, you could think of two different directions. Either you say, I'm going to study a problem that has a matroid in its explicit definition. For example, this has been called framework, so that this is kind of co-option of a term which was slightly differently used. For example, you could just think of as a combinatorial / algebraic problem. We have a graph with a matroid defined on its vertex set. Is there a path from S to T whose vertex set has rank at least k in the matroid? This can be done in 2 to the k time if we work on a characteristic 2. And you can encode a bunch of other specific combinatorial questions into this, like, is there a path which intersects all of these k different vertices along the way? Is there a path which contains vertices of at least k different colors? Or, the general thing. In the other direction, there are so this is where you explicitly have a matroid in the problem you're trying to solve in order to generalize. In the other direction, there are some problems, in particular like finding a directed cycle of at least k vertices, or some more obscure ones like can you modify this graph in at most k places such that the result is Eulerian, which includes being connected, where you can use matroids as a support to speed up the dynamic programming to get a faster algorithm than we would have been able to do through pure combinatorics.
Could you elaborate what you mean to use matroid as a support in dynamic programming?
I mean, well, if you look at the Eulerian, like, can I make k changes to the edge such that the result is Eulerian? That means all vertices have even degree and it remains connected. So if you work over the co-graphic matroid to tell you which edge sets do or do not disconnect the graph, then you can kind of, there are some so these are two categories of underlying algorithm. The first bullet point is basically the representative set theorems. We can do dynamic programming with fewer sets saved. The second one is a kind of seemingly, usually more powerful kind of polynomial seeding. I'll get to them if I have time. It's, I'm really I might have tried to pack too much into this talk. But there are some, the general point I want to make was just sometimes you can use the linear algebra encoding of combinatorial properties to speed up an algorithm, even if you're not interested in the linear algebra properties a priori. In the same kind of direction, in cardinalization, like one of the results, if you have a graph with a set of k terminals, you want to have a smaller graph on the same terminal set, okay, which has the same path packing number for all participants of terminals. I'm speaking this too quickly, but there's some kind of, you can use matroid theory to encode combinatorial information in very sparse space. So these are kind of some applications we have seen for linear matroids. All of this is usually most powerful when it's linear. So I will be talking about how many of these translate into a delta-matroid version. So I'll start by saying something about what on earth are delta-matroids, of course. But then most of it will be about the polynomial time and representation issues, and a few words about parameterized properties in the end. So I'm going to illustrate the difference between matroids and delta-matroids with this graph. So it's a fact that given a graph, there is a matroid whose bases are exactly the vertex set of maximum matchings. And there is a delta-matroid whose feasible sets are exactly the endpoints of matchings in the graph. So in this particular graph, the matching matroid, usually the first time you encounter it, sounds interesting, but when you look closer, you realize it's a disappointment. This graph has, so a quick check, what is the matching matroid of this graph? Well, since it has a perfect matching, it's just all subsets are feasible, no information encoded. The delta matroid of this matching thing encodes the fact that, well, empty set is matchable, there is an edge on A and B, there is an edge on A and D, and so on, and in the end the whole thing is a perfect matching. So the difference between matroids and delta matroids, these are feasible sets, they have different cardinalities, not all subsets of feasible sets are feasible, but some subset might be. So we're going to talk about linear, So just a few categories of delta matroids that will be useful in applications. Any linear matroid, you can take the basis of them to make a linear delta matroid. You can take, well, when we get to twists like symmetric modification, differences of the basis with some set. The matching was just presented, and one which is combinatorially very either useful or cute is they can ask a feasible set as a vertex set such that if you remove them from a graph, the remaining vertices have a perfect matching. This turns out to be useful in some combinatorial settings where you're you're looking to pack, for example, a lot of copies of K2 and in addition something else. You can encode the lot of copies of K2 into matching dual delta-matroid. One special case of the matching delta-matroid, if we have a ground set which is just right, I should be using the pointer for pointing. If we have a ground set which is partitioned into pairs, we want the feasible sets to be all sets which contain both or neither member of every pair. So Ui if and only if Vi. This is the matching delta-matroid of the graph, which consists of n disjoint edges. But combinatorially, we can use it as a constraint to. Wrong button again. In combinatorial application, we use this as a constraint to say we're looking for sets where both of these members are in or none of them is in. And as a preview, if you think about combining two different pairing delta-matroids on the same ground set, they induce a partition of a ground set. We're saying you have to take all of these k-half elements or none of them, for example. I'm not going to dive deeper into this, but this turns out to be, when you're looking at hardness results, this innocent thing turns out to be one of the most difficult to handle in algorithms. This is one of the sources of hardness, the fact that you can do this. Questions so far?
So dual is just twisting by whole set, right?
Yes, dual is just a set complement of whatever was feasible.
Mm-hmm.
So we are right. So first, I'm going to talk about representations and constructions of linear delta-matroids. We're going to use this to show some algorithmic results, matrix multiplication time, so it's all randomized, it's all over large fields and so on, and some brief look at the FPT properties of these problems. So the canonical example of a linear delta-matroid might be the Tutte matrix for matching. So a skew-symmetric matrix is a matrix where A transpose is negative A, so whenever you have an entry, top right corner x3, bottom left corner is its negation. So on the right-hand side, here's the same graph on 6 vertices with labels on its edges. On the left is what's called the Tutte matrix of this graph, where it's adjacency matrix with non-zeros replaced by variables, and these variables are just formally independent variables over an arbitrarily large field, so you have no interference, no cancellations. But it is a fact that for a skew-symmetric matrix, the determinant is the square of a polynomial called the Pfaffian. The definition of the Pfaffian is sum over all perfect matchings of the support graph. The support graph just is the graph whose edges are exactly the non-zero entries of the matrix. So sum over all perfect matchings of something times a plus minus 1 sign term times the product of the members of the edges of the matching. So in this example, this graph has 3 perfect matchings, so we get 3 terms in the Pfaffian, edges 1, 5, 7, or 2, 4, 7, or 3, 4, and 6. And as I said, if these are algebraically indeterminate variables, as long as you have at least one term, the Pfaffian is going to be non-zero. And this is why the Tutte matrix here encodes the existence of matching in the graph. In order to get this into a delta matrix, we say that we consider that the edges and columns of the matrix are labeled by the grounds of V. And then we ask, like, okay, if we take this submatrix of a 2 by 2 in the top left corner, is that submatrix non-singular? Right. So if you have any skew-symmetric matrix, you just collect the subset of V which induce a non-singular principal minor that is a delta-matroid. A linear matroid is that in combination with twisting, where twisting means you start with the natural kind of encoding of all feasible, all non-singular principal minors, and you take symmetric difference with some set S for all of them. So this in the literature is the classical representation. What is a linear delta-matroid is it's a delta-matroid which can be encoded as some twist over the set of feasible sets in some skew-symmetric matrix. It is a fact which we won't need in detail, but if you have the twist in the set definition has an algebraic correspondence. If you're trying to do a twist with some set S where a S itself is non-singular, you can write down a different matrix on the same ground set which exactly encodes, like feasible sets in this one are exactly feasible sets in this one, delta S. So you can kind of twist the matrix around to change its behavior.
Maybe something's missing, right? Anyway, it's not skew-symmetric at the moment.
I think
so minus C transpose times B inverse.
I think is I don't know. There might be a sign error, but it also secretly uses the fact that B itself is skew-symmetric. So there's a sign term which corresponds to a transpose something. The details will not even be necessary. So just it exists. So now this is the first new result I'm going to talk about. So twist representations are annoying in algorithms because you have to remember whether every element you're working with is positive or negative, whether it has been twisted or not twisted. So we have a different representation. So we start with some arbitrary So we start with some arbitrary linear delta-matroid, which is this matrix twisted by S. And first step, we're just going to add a artificial set of cardinality S new elements. And this is an identity matrix. So this is just, we connect, these correspond to negated copies of S in some sense, but of course, we're allowed to do this. We're just adding new rows and columns to the matrix we have. Then we observe that S union T here is something identity minus identity something that is obviously non-singular because it has only one matching. It's just identity matrix. So you're allowed to compute the twist. If you go through the algebra, you get this matrix where if a set which is feasible here is feasible if and only if F delta S union T is feasible on the right hand side, and delta S union T means forget about S and change it in the condition we want to insist that you have to use T. So instead of twisting this by S, we're contracting T over a larger matrix. You can go both ways. So this is a linear delta-matroid has like every classical twist representation can be turned into contraction representation in matrix. Well, just by doing this rewriting. And if you have a contraction representation, you want to get back into a twist representation by some pivot, some matrix modifications.
So can you repeat? So you construct the matrix on the right from the left?
Yes, starting from the top left here, of course, the entire matrix on the right is determined by just shuffling elements around. And this matrix, contract T, represents the same delta-matroid as this matrix delta S. So every linear delta-matrix can just syntactically be given a contraction representation where instead of a twist inside the set, we have an external set of, I don't know, k further elements that you have to contract. And we would like to claim that this is much more useful for algorithms and also actually has some nice consequences for constructions.
Oh, question?
Yeah.
So the reason that you want to keep the contraction representation is because you cannot, from the right-hand side matrix, you cannot get another matrix on just V.
I could, I mean, okay, if, where are we? I could, if I wanted to contract T and remove them from the matrix, I would have to expand T into a feasible set. Because T, okay. If this submatrix were non-singular, then we could do so, but then we could also twist by S in the first place, because this is the same submatrix. Normally, we might expect that maybe it might even be that this is just a zero submatrix, and then if we want to twist, we have to expand it into a feasible set, which forces us to go back here into carrying around the twisting set. So we can always assume, if we want to, we can always assume that this is actually zero, but just taking some feasible subset of it and twisting within T and then deleting. But we won't care too much about how many elements we have. We can, if they become too many, we can reduce them down, but basically the number of contraction elements will not overwhelm our algorithms in any place. So I'm going to argue that one illustration for why contraction is easier and nicer than twists. So we have the problem of finding a max weight feasible set in a delta-matroid. Your input is a delta-matroid, where it's going to be linear, and you have weights which are positive and negative on the elements. You want to maximize the weight of a feasible set. If you remember from matroids, we always assume that the weights are non-negative, and we assume that our final answer is going to be a basis of the matroid. So if we had the negative weight, we just lift everything by the same amount. But if our feasible sets have different sizes, this would change the weights in different ways for different sets. There exists a polynomial time algorithm for computing a max weight feasible set in delta-matroid. This is some signed version of the greedy algorithm, which will be a sequence of n steps of what's called separation oracles. N queries, each individual query will take n to the omega matrix multiplication time to check linear independence or something. So the kind of textbook, or there's no textbook of this, but the Boucher version of this would be n to the omega plus 1 time, because we repeat n times matrix multiplication. And we could define a recursive algorithm with some or various tricks to get it into matrix multiplication time directly. And I'll say that because we actually did that in the first version of the paper until we realized we didn't have to. But you could also just reduce it back into matroids now. So the algorithm would look like this. If we define n to be all elements with negative weight, we twist our original matroid by this set of elements, and we change those weights from negative into positive, which corresponds to saying instead of having two sets of negative and positive balls where we have to find a max weight set, we just start off with a bucket with all of the negative elements already in it, and each step we either remove a negative element or add a positive element. So that's why this twist makes sense, and in the end we just deduct the value. Now we get the representation of this delta matrix as a contraction over a linear matrix. And a linear matrix can be directly interpreted as a representation of a linear matrix if you only look at the columns. So now we're just looking for a max weight basis of this matrix, which includes all elements T prime, which of course we can do with textbook algorithms from the literature. So if we had twisting sets still around, we would have to do something to remember, are we allowed to keep this element? Maybe we have to throw it away and so on. But this all turns into complications coding into the contraction set. And yeah. So this all becomes a matrix multiplication time, because that's the time it takes to find the Lex-min basis of a matrix. So yeah, this is not meant to be a groundbreaking result, it is meant to be an illustration that contractions are nicer to work with. So, another fun thing. There are some operations over. What was the question? Right. There are some operations over delta-matroids which define new delta-matroids. The most intricate one is one on this slide. You have two delta-matroids. They just define a new delta-matroid where the feasible sets are symmetric difference of something feasible in the first one together with something feasible in the second one. So Boucher and Schwarzler showed in 98 that for any delta-matroid you start with, you get a new delta-matroid in the end. And we will show that if you start with two linear delta-matroids and they are represented over the same field, well, field over the same characteristic, because you can just go to an extension field, then the delta sum is also linear. This is quite a powerful kind of tool for building new delta-matroids out of existing ones. And so this is going to be right, so I'm just going to show a picture. I hope it's not too overwhelming. So our input is two delta-matroids which we are assuming are given in contraction representation. The picture doesn't include the contracted elements, but you can imagine they all sit on the side on a set of elements which have to all of them be included everywhere so they don't interfere with each other. So A1 is a matrix that encodes the first delta-matroid. A2 is a matrix which encodes the second delta-matroid. Then in addition we have three different variable sets. So this is a matrix where diagonal is a set of variables yv, 1, which are independent. And then the y2 is a second set of variables, and y3 is a third set of variables. A better picture is to the left. The first delta-matroid is encoded into the induced submatrix here. The second delta-matrix is encoded here. And original elements induce a zero matrix. And then we add on top of this a collection of variables, like independent variables, which encode edges between the first and the second copy, second, third copy, or first and second copy. And if we think algebraically about what one term, or what the Pfaffian looks like. So this is a trick we're using everywhere here. We're working over arbitrarily large fields. We have no cancellations between monomials except the kind of identical monomials can cancel depending on the coefficient. Since all of the y variables are distinct variables, we can look at kind of just one arbitrary collection of y variables which are used or not used in one particular matching. The only cancellations which can happen is with respect to matchings on the elements that are not matched in that particular edge set. So in this scenario, we're using the variable number 1 between A and A1, variable number 2 between B and B2, variable number 3 between D1 and D2. So every term the Pfaffian is a perfect matching of the underlying set. So this eliminates all the endpoints on the red edges, and what remains is a feasible submatrix on A2, B1, C1, and C2. And this part without the y variable is just a direct sum, which means A2 and C2 are feasible in D2, B1 and C1 are feasible in V1, and in terms of why it's a delta sum, on the left-hand side we say we do have a copy of A and B, which means that exactly one out of A1 or A2 and one out of B1 and B2 is matched to B, so exactly one of those copies is in the feasible set. Down here we either have 0 copies because we use the red edge, or both copies C1 and C2 are in the feasible set. So the variables encode exactly the trace of members of the first, second, both, and neither of every element in the ground set. And this thing, if you trust me on this, the Pfaffian of this thing with, for example, A, B, and everything in V1, everything in V2, and everything in T1, everything in T2, is non-singular if and only if there exists a feasible set which contains one copy of A, one copy of B, and an even number of copies of C and D. I realize this is kind of a lot to take in this quickly, but this is kind of there's nothing more hidden here. Like if you all had 5 more minutes or 15 more minutes to kind of work through the arguments, I think you would arrive at the same conclusion. Like we're asking what are the terms of the Pfaffian of this matrix. Because the y variables are algebraically distinct, we're allowed to ask one collection of y variables at a time. What are the terms with this particular fingerprint in the y variables? And those turn into exactly requiring one copy of every element that is in the feasible set A, B, and then 0 or 2 copies of every element that is not present within V. So we move from contraction representations A1 contract T1, A2 contract T2 into the new bigger matrix contract V1, V2, T1, and T2. So we're contracting like 4 times more than the ground set. If that's a problem, we can once again just simplify and transform the matrix. But in terms of polynomial time constructions, we're not even transforming the matrix. We're just writing down the larger matrix and filling it with variables. So in particular, I've forgotten to say this. That this is what, if you want to move from variables to concrete values, you invoke Schwarz-Zippel to say I'm going to work over a field which has a large enough number of elements in it. Which means we go to an extension field over a base field until we have, let's say, an exponential number of values available. And then we just randomly evaluate every variable, and almost certainly if we're a big enough field, we never accidentally make anything dependent that shouldn't be. Among the footnotes, doing so incurs a polynomial time overhead on your operations. Because whenever you do matrix multiplication operations, you suddenly have to multiply by the representation size of the base field. In the paper, we do this much more carefully by kind of analyzing the exact effect of algebraic mistakes by working over smaller fields. So you can get randomized algorithms which are correct with a probability 1 minus epsilon and not pay a significant overhead. But that's not, here I just want to illustrate the existence of the linear representation.
So when you have a 2 delta-matroid representative over, let's say, field of size Q, and then when you do this thing, then the size of field you require depends on the size of the delta-matroid, right?
If I want to be able to tell you there's a non-zero chance that it's an exact representation, you would need to give an extension field of the same characteristic with at least exponential number of elements in the field.
I see.
So if you worry about only binary or only specifically size 4 or something, this doesn't tell you anything.
Right.
But that's the same for matroid union, right? Matroid union requires arbitrarily large fields because you can encode arbitrarily large uniform matroids with it.
I guess you don't know how to de-randomize, right? Because
I don't know how to de-randomize anything. The entire talk is randomized. I think that's a really difficult question here. This is, I guess it's not formally as difficult as arbitrary polynomial identity testing, but I'm not sure it's much easier in practice. Like even some very interesting matroids like gamoids, we were very happy if we had the deterministic representation of them, but it's just very difficult.
So is this another example where, like, instead of twist representation, like contraction operation is representation?
I mean, I don't think we would have thought of this option if we didn't think in terms of contraction representations. Like if your delta matroids were represented with twists, I mean, since they're equivalent, there exists a set of steps which would have the same effect in twist representation. But this is just so much easier to think about. Just throw everything in the contraction set and think about this matchings over a collection of triangles. Right. There was one other I didn't go through in detail. It's easier. There's something called union of delta matroids, which is disjoint union of F1 and F2, which also has a linear representation. The easier version of similar tricks. Any questions on this part? So, just kind of. Right. So the next thing to talk about would be the polynomial time solvable problems. So here, the funny thing about delta matroids is all problems that can be defined over delta matroids are equivalent to one another. So in matroid world, intersection and parity are two very different problems. Intersection, I guess there are two delta matroids that want a common feasible set. Parity, we have one delta matroid and a partition of the ground set into pairs. Want to find a feasible set, which is a union of pairs. The empty set is a legal option if your delta matroid, if the empty set is feasible in the delta matroid, but it might not be. So you might have to break some pairs. And another thing, you can also ask, like, find me two elements F1 and F2 to maximize the cardinality of the symmetric difference. All three of these problems are as difficult as linear matroid intersection. In the first case, if you want to reduce intersection into parity, we're going to construct the disjoint union, direct sum of D1 and D2. And the pairing is just the two copies of the element or one pair. So now you want a feasible set that either contains both or neither copy of Vi for every element Vi of the ground set. So parity is powerful enough to express intersection. Maybe it's not a big surprise. In the other direction, parity is exactly the intersection of the delta matroid with this pairing delta matroid d pi. So delta matroid parity reduces back into delta matroid intersection because the pairing constraint is a delta matroid constraint. Which means if you have no other assumptions, if the only thing you're given is two delta matroids and a separation oracle on them, then you have no hope. Like, you will need exponential time to solve delta matroid intersection. And the problem of delta matroid intersection is NP hard because the problem of matroid matroid parity on non-linear matroid is NP hard. And the third one, delta covering, if you want to maximize symmetric difference, we want to minimize the intersection of D1 and D2 star. I mean, I'm not doing that one in detail, but if you can dualize one of them, the difference turns into being the same thing. So, basically where we have only one problem to solve, and we have to assume linear delta matroids to be able to solve them. There's a little bit of cheesiness in this notion of parity. Okay, probably better to talk about that in one next slide. Is there any question on these problems?
So
yes.
this delta covering problem, why is it called delta covering?
Because covering was defined as maximizing, I don't know, either union or cardinality or disjoint union. Then delta sums is the same thing with the delta operation. I'm not sure.
In a sense, you said that this delta sum of delta matroid is a delta matroid, right? So
Yeah.
the delta covering, in a sense, is to find the maximum cardinality feasible set in
Right.
the delta sum, right?
Right. So yeah, you can probably get a sense of what the, once we have a representation of linear delta sums, you can sense what the algorithm is going to be for detecting them, right? You construct a representation, you ask for a maximum a feasible set in the result. Any other questions? So, right, from the literature, Galen, Evata, Morota, linear delta-matroid parity can be done in the paper they write n to the 4 time. If you're kind of picky about running times, the bottleneck is matrix multiplication operations, which means their algorithm can be turned into running time n to the omega plus 1. They solve a variant of the optimization problem, which is if there is no feasible set with no broken pairs, we can minimize the number of pairs where f contains only one member but not the other. This feels like the wrong optimization version. It feels like what you want to ask is just give me the biggest union of pairs that is feasible. But that's a harder problem. This one still contains the matroid parity problem of give me a maximum independent set that is a union of pairs. Because if you think about it, if you have a maximum independent union of pairs, you complete it into a basis, you have to break exactly rank minus k pairs to get to a basis. So if you only work over basis, you solve the correct optimization problem over matroids by solving this one here. And through more or less standard methods that I'm not going to give in detail, once we have a linear representation for delta sums and so on, we can solve, clearly we can solve the decision problem of asking what is the biggest, does there exist a common set, and if not, what is the number of broken pairs, just by rank question of the linear delta sum. What requires a little bit more work for people in the area, this is methods of Harvey. You can get to a search algorithm which actually finds a solution in time n to the omega. And that also includes this version of search. And we can also solve the other optimization version. Like if we, in time n to the omega plus 1, we can find a common feasible set of maximum cardinality, or kind of a union of pairs which is feasible and has a maximum number of pairs. Or we can do a weighted version by kind of usual pseudo-polynomial overhead on weight dependence. Both of these are just algebraic tricks of the fact that the Pfaffian of the matrix I showed you a minute ago, its variables give an algebraic footprint of how large how many elements were in the common intersection. That's exactly the element, but that corresponds exactly to the number of edges of type 3 that were included in the set. So you just trace the coefficient of minimum number of elements from y sub 3, and this gives you maximum cardinality intersection. These last two, maximum cardinality intersection, was an open question of, let me actually forward so I don't misspeak. Okay, I'll get this. Maybe I should ask you, were there any questions on this? So we speed up the algorithm by a factor of n at the cost of being randomized, and we solve this more general maximum cardinality version. Again, we have no idea how to de-randomize this. This is, I forgot to talk. A few pointers. I couldn't resist kind of just putting keywords on the slide for people who know something about this. Right. So we mentioned the contraction representation. mentioned but did not prove that the union and also the delta sum of linear delta-matroids forms a linear delta-matroid. There is something you can define which is a projected linear representation. We have a further set of elements where we say you can have any intersection with these elements x you want. I only care about your intersection with the main set, which gives you a little bit more expressive power because you can do, well, independent sets of matroids, for example, encoded this way, can be reduced into projections where the existentially quantified elements have cardinality 1. Which means you can suddenly just ignore, you can just assume that maybe there is an existential projection, maybe there isn't. Just an exhaustive guess on whether the solution is going to include or not include the extra element x. This is just a delta sum of the kind of, let's say, uniform delta matrix, or even just matching delta matrix of the complete graph on x. So whatever fingerprint you had on existential quantification, I can cancel it with a delta sum of some feasible term from a matching, and the only thing I need to keep around is one element to keep track of the parity. Yeah, the algorithms, as I said, max weight feasible set, n to the omega by reduction to matroids, delta-matroid parity, n to the omega randomized, and the names I forgot were Kakimura and Takamatsu. That 10 years ago, they had some applications of constrained matching problems where they wanted to find the maximum cardinality and delta-matroid matching. And they had some limited cases, but this is a general case randomized algorithm. So this is the kind of polynomial time algorithms part of the talk. So it's going to be a very short overview of what the results look like on FPT half. But once again, I'll pause and ask if there are questions on this. So as you can probably tell, like the representation construction is the part doing the work here. Everything else kind of follows by. I mean, there is work involved, but all of that is just reading the right papers and figuring out how it works in your case. Okay. So now we're going to ask, what about FPT algorithms on linear delta matroids? So how does the timing work here? Do I stop when 30 past, or there's a bit of time lost in the shuffling?
Yeah, I think you can continue, right? Because we really had some delay in the beginning, so.
Right. So I won't be able to talk about the technical details in this, but there's 2 sets of results and I want to sample them both. So for FPT, first we look at the 2 sets of problems. So first we just look at the most natural question you can consider asking, maybe. Like if I have 3 delta matroids, I'm going to take the intersection instead of 2 delta matroids. Or maybe instead of parity, I have sets of cardinality 3. I'm going to take a union of k triples, and the union is feasible and so on. Over matroids, all such questions are FPT. Over linear delta matroids, we get an enormous difference depending on whether your parameter is the cardinality of the set you're looking for, or the rank of the representation. Rank just means largest feasible, cardinality the largest feasible element. For those who know matroids, you never see a difference between cardinality and rank, because if your matroid has larger rank than you need, you can always truncate it to a different matroid whose rank is k, and otherwise has no changes. Over delta matroid, this is very much the opposite are true. So even really simple cases of intersection of 3 linear delta matroids are hard problems, parameterized by k alone. If your parameter is that my delta matroids have not very large rank, then there are some very powerful algorithmic methods that tell you that your intersection and set packing and a bunch of other things are FPT. Right. So the first thing I'm gonna say here, which could just give some sense of what's going on. What is a linear delta matrix of bounded rank? What does it look like? So let's assume let's assume it has no contraction. It's just a kind of empty set is feasible. So it's just represented by a skew-symmetric matrix. If you get an arbitrary delta-matroid of bounded rank and you just look at it visually with a normal human eyes, you won't see that there's anything strange about it. It can just be a bunch of arbitrary elements all over the place. But if you take a maximum feasible set like a basis and you perform this pivoting twist operation, you can realize that if this is size r and this is size n minus r, the vast majority of that twisted matrix has 0 entries. Because if there were anything down here which was non-zero, this would mean that A star index u comma v would be non-zero. This would mean that the submatrix on elements u and v of A star is feasible, non-singular, because as a matching is just a single edge. And this means that this delta uv, which means b plus u and v, like an even bigger set, is feasible in the original matrix. So if we want to work on contraction form, we can do so. So that means a bounded rank delta matroid can be represented as R contraction elements and an all 0 matrix except on the contraction part. If the top left set here is also 0, then this is exactly a matroid. But if the top set, because everything that happens is interaction between T and the rest. But if this is non-zero, then some subsets of this could still be feasible if you pad them with terms from T. So it looks a little bit like a linear matroid representation of bounded rank, except you carry around one more R times R complication that encodes something extra. So as an open but not formally phraseable question, but just looking at what we can get combinatorially out of expressing things as bounded rank linear delta matroids, it looks like they are in some sense not that far away from linear matroids with an additional guessing step. I do not have any formal version of that statement that actually carries through. So if there's even more to say than just this representation form, that'll be interesting to hear what that means. But I am unable to form a coherent conjecture that isn't immediately rejected by counterexamples. If you want one example of a linear delta matroid of bounded rank other than a matroid of bounded rank, you can first think of the matching matroid, delta matroid for a graph with bounded vertex cover. Like again, if your vertex cover is also independent, then this is basically just a transversal or something like a well-known matroid cases. If the vertex cover has internal edges, then you get some behaviors, some subsets of the rest are feasible, some are not. And you can also start from a matching delta matroid and contract something until only a small portion of the remaining vertices are allowed to be modified. So you can do some things with matching matroids, matching delta matroids to get bounded rank delta matroids. Right. So I'm just going to name the existence of the algebraic workhorse here, which gives us our FPT algorithms. This was a result presented at this year's SODA. This is kind of a distillation of things which were in various forms used in the literature, but this way of phrasing it, I think, is a very useful phrasing. So we are going to solve this as a this is a kind of problem setting. You have a, well, let's say multivariate generating function, or just some polynomial of degree k. You're able to evaluate it. This might be a determinant or something. This might be, I don't know, entries of a power of a matrix, or anything you have a efficient evaluation for, but with just very many terms. And over the same ground set, you have a linear matroid. We want to know if there is a monomial in the monomial expansion of the polynomial, which is multilinear and is the basis of the matroid. We can do that, if you're characteristic 2, we can do it in polynomial space 2 to the k evaluations. If you're over other fields, you have to use exterior algebra methods, which are also previously used. 2 to the order k time and exponential space in that case, to kind of test whether this polynomial has a term that is basis of the matroid. So like we talked at the start of it about using matroids as generalizations, like if your question was, is there a path from S to T which is also independent in a matroid, then you can let the polynomial be walks from S to T of length k. Walks are easy to evaluate. You just write down the adjacency matrix with variables in the entries. You take its power k. You look up one kind of entry, or like the S comma T entry of that power. This will be the walk polynomial. You can also get it in other ways. And now if we insist that the walk polynomial is also multilinear, then it's a path. And we can, in addition, say we want a path of length k, which is independent in a matroid. For example, uses k different colors, or and so on. And we get it almost for free, because this is the same running time as was previously used in multilinear detection or constrained multilinear detection, as has been published. So this is kind of powerful way of phrasing things. And the delta-matroid version is a kind of search and replace version, where you replace the rank by cardinality by rank. If you have some multivariate polynomial and a linear delta-matroid, and the rank of the delta-matroid is R, in the same kind of running time, like 2 to the R evaluations of the polynomial, we can test whether there's a monomial in the polynomial which is feasible in the delta-matroid and multilinear. Again, if this were a matroid, it would replace R by K by truncation. Over delta matroids, we very much cannot do that. So this is some kind of additional expressive power. And here, for example, if we want to solve the intersection of 3 linear delta matroids, we need a polynomial P for the intersection of the first and the second. And we just put the third delta matroid in the delta matroid layer of this thing. No, I'm not going to do proof sketch. I just want the application. So remember what the construction of linear delta sum looked like. Now we are going to, so in that construction, we are going to not use any of the ground set elements here, so everything on the left side is grayed out. Now there are 2 choices for our element on the right hand side. Either you use the edge from Y, or you don't use the edge from Y. And these are the terms of the Pfaffian of V1 union V2. So kind of the variables where you don't include the Y variable are those which are feasible in both V1 and V2. So if we take the dual of D1 and the dual of D2, we make this construction. The signature, the fingerprint in the Y variables will enumerate all intersections of D1 and D2. This is our polynomial. Within that polynomial, we are looking for terms that are also feasible in the third matroid. So D1 and D2 have arbitrary rank, because this is just an algebraic construction. D3 has rank R, because that allows us to use the sieving. So rank of third layer is 2 to the order R time for 3 delta matroid intersection. Is the algorithm here clear? It's just this is just how all of these applications work. Like you have some polynomial which kind of does something useful, then you add a delta matrix on top of it. Summary of these problems. So like if you want an intersection of two linear delta-matroids, then that's in polynomial time. If you want an intersection of two linear delta-matroids and a matroid, that's 2 to the order k time. And if you want to intersect three linear delta-matroids, the W1 hard on the cardinality parameter. And over rank parameter, we can do, well, intersection of arbitrary number of delta-matroids or some set packing problems and so on. Because basically anything you can encode into a generating polynomial, the way we just did, you can always just add the bounded rank delta matrix on top of it and keep solving your problem. And yeah, I mean, I promise not to try to do the proof for this evening, but it's not that hard. Like the algebra, we want to emulate a Pfaffi and we want to emulate the sum of all perfect matchings of some support graph. Perfect matchings are, I claim, the same thing as product of quadratic terms which are multilinear and cover the entire variable set. So we decorate the variables of a polynomial with some artificial variables, and then we multiply everything out and we extract the coefficient of y1 times y2 times up to yr, and this carries in characteristic 2. This carries exactly the Pfaffian because we didn't have to worry about signs. Questions? So I said there's a second set of results which are a bit of a surprise. We're going to define a problem which is a linear delta matrix together with a combination of triangles, like subsets of the ground set of size 3. They're not a partition, they're just any arbitrary combination. You could think of them as being triangles in a graph, but they don't have to be. They can be just arbitrary sets of size 3. We want a feasible set of cardinality at least k that can be covered by a triangle packing. So there exists some set of disjoint triangles where you need at most k of them, such that the ground set they cover has rank at least k. This is FPT, and it really shouldn't be. If you're following what's happened now, looking for a ground set which is exactly partitioned into triangles is W1 hard. And probably your first idea towards solving the triangle cover problem is to try to reduce it into partition. But yeah, the fact that the partition is hard looks like it should easily be possible to show honest proof for this one, but the covering is just gives the system more freedom. The algorithm for this one is a combination of kind of guessing step, like if in Prometheus complexity we do a lot of color coding, we kind of guess behaviors of things, together with some algebraic methods to simplify the results. If I say one keyword about what makes it work, you can think of if you have one element which is in the center of k plus 1 or 3k plus 1 otherwise disjoint triangles, you will always be able to grab one of those triangles to cover that element and not interfere with the rest of the solution. So that gives you a notion of a safe element that we can algebraically reduce or contract. And if you're not safe, then you have a bounded matching number, and you can start guessing at least one partner of every vertex, because your vertex cover a size k in some graph, and then you can keep guessing and keep modifying. So a couple of consequences. Well, the first example of what you can do. Well, this is a problem which you can solve by other methods, but it reduces into the triangle cover pretty easily. You have a delta-matroid parity setting where you pairs come in colors. You want a solution that uses exactly one edge of every color. This can be done with the monomial sieving ideas, but it also reduces into triangle cover by just adding one more ground set of k different elements, one element for every color. An edge UV of color I becomes a triangle UV ZI. So it's pretty close to to this kind of rainbow delta-matroid parity, and in the end our algorithm reduces back down into this one after a bunch of guessing. Another one, which is kind of if you make the delta-matroid we're talking about be the dual of the matching delta-matroid, then you start asking, is there a union of triangles whose complement has a large matching number? So one problem which I'll ask you to take my word for it that if you let D be the dual matching delta-matroid and the triangles be exactly the K3s in a graph, your problem is solving, is there a packing of K2s and K3s whose number of edges is at least K more than the matching number of the graph? This can be generalized into asking, is there a cluster graph, given a graph with a cluster subgraph on at least matching number plus K edges? This was an open question. The Crespel et al. This is the big survey on edge modification problems. It was considered in the literature not known to be FPT. It is FPT here because if your graph contains a large number of K4s, you can just keep grabbing those and increasing your excess parameter. Once you run out of those, you have a modulator into a K4 free graph where you're solving exactly this bullet point problem of K2 and K3 packing plus modulator. The last one, which we're applying here, strong triadic closure. It's some notion you want a set of edges that whenever your set contains a P3, then the third edge has to exist in the ground graph, but not necessarily in your set. I'm not sure about the history of this problem, to be honest, but it was considered by two different sets of authors as an open question of whether that is feasible parameter above matching. We find it is FPT in K4 free graphs by a more complicated version of the same type of guessing color coding algorithm. We find it's W1 hard in general, and the hardness proof very much consists of trying to get an algorithm, finding a case we can solve, and getting a W1 hardness proof out of that abstraction. So this was again kind of open question from the literature. So we get an FPT approximation, but not actually an FPT algorithm. So yeah, I don't know what to think about the generalizations or proper direction to take this problem, because if you ask about a feasible set that can be covered by K4s, then again it's W1 hard because you can encode triple, like 3 parity into that. So this is a kind of odd feasible corner that I don't know how to think about it. So this is the last thing I'm saying. Some summary, like intersection of 2 delta-matroids in a matrix, once again 2 to the order cardinality, 3 delta-matroids 2 to the order rank, covered by triangles k to the order k FPT, triangle partition and set packing and so on 2 to the order rank, W1 hardness for intersection by parameter k, W1 hardness for cover by K4, W1 hardness for partition to something else. Yeah. Yeah. Thank you for your attention.
thank you. You went very wrong, but anyway.
Oh, it was a bit over time, but
Yeah, but anyway. Any questions?
So when you prove the hardness, like, can you make a typical example of the how the hardness?
right. Yeah, it's well, it's a reduction from k-click, because of course it is. So we have two layers which are just pairing delta-matroids, which allow us to say for every vertex color, for every edge we want to select, we of one color, we have to select k different copies of it. And then we have one delta-matroid, which is basically, apologies to video people, this is an intersectional constraint saying so formally this is a twist of a partition matroid. You take a partition matroid on one copy of xi and then a bunch of further copies of an edge of that color. If you twist it to one element, you say, I choose a vertex v in color I if and only if I also choose an edge which matches this identity between sets I and j. So this is an intersection of, if you've been playing along, three twisted partition matroids, which is three twisted regular matroids, easiest possible linear matroid, and it's still W1 odd. This can also be described as a matching delta matroid over some other graph. Yeah.
Maybe a bit of a naive question, just because of the way you defined the delta matroids. Does this give you any way to estimate or compute the permanent?
Probably not. I don't know. I mean, the Puffian has, if you're working over anything not characteristic 2, the Puffian has a bunch of sign terms, same as the determinant.
Yes.
And I work most of a characteristic 2 because I don't have to understand what the sign of a permutation means.
I see, that makes sense.
Right. Any other questions? All right. If not, let's thank the speakers.